think we're ready. We're going to do a little bit of SolidWorks stuff today, and assuming there's time at the end, which there should be, we'll look at this problem a little bit. There were at least one question about it, and it's got a little bit of a trickiness to it. It's worth looking at, I suppose, so we'll look at it a little bit. But first, we're going to do a 3-point bin test simulation in SolidWorks. So this would be lab 2 if we were in person, little rectangular bars of whatever material we were interested in, and do a 3-point bin test. So it looks like this is kind of what a 3-point bin test might look like. You can get the 3 points. There's 2 supports and 1 load in the middle, and so that's the 3-point. There is a 4-point bin test also. I don't see any pictures of that. Basically, there are 2 loading points that are kind of spread out in a 4-point bin test. None of these look like. Well, here's some 3-point bin setups over there. So this is what we're going to simulate in SolidWorks. There's a couple of little details that we need to make sure we do correctly, or you'll get incorrect results, and they might not necessarily look incorrect. In fact, I was noticing, for whatever reason, maybe I did this on purpose, I don't know, but the last time, the picture that I posted here actually has some incorrect results. Look at that S-shaped curve there. That's not right. So I'm not sure why I posted that picture to go with it or not, but that's maybe to get people to like, well, that's not right. But yeah, we're going to avoid that, hopefully. So let's go in and let's go to SolidWorks. There. And we're going to start a new part. File, new part. And what we're going to make for our part is just an 8-inch long, 1-inch wide, and 1/8 inch thick rectangle. So let's go over here to extruded. Let's do the top plane, and let's just make a rectangle. And then let's dimension it where this, I think my units, oops, didn't get the dimension on there. There we go. I think we're in inches, so let's do 8 by 1. I'm not sure what the actual test sizes are supposed to be for this, but 8 by 1 will work for what we want. And then let's make it an 1/8 inch thick. That also doesn't really matter. What that would simulate is if we were doing like we were physically go and build a truss, 1/8 inch masonite is what we usually make it out of, laser cut sheets of that. So there's our little part. Let's do one more thing before, actually let's save it, because I did have SolidWorks crash on me a little bit ago, so just in case, it doesn't take long to make that part, but just in case, we'll save it. All right, now there is another thing. I want to put some reference not curves, I want to put reference planes in here. So I'm going to put one, that'll be the reference for it, and then let's inset it a 1/2 inch. What this will do is I'm going to make a split line here so that I can actually apply the support at this point. End over here to reference. And then let's put this one in the middle, so that'll be 4 inches the other way though. Okay, and then let's put one on this end. So reference plane. This one will be another 1/2 inch in. Oh, not 5. 0.5. There we go. Okay, now I've got the planes. That's not enough by itself though. Split line. So I'm going to do curves, split line, and we will select the 3 different planes here. They're going to be hard to select that way. Actually, I'm not in the plane. There we go. There's plane 2, and there's plane 1, and then we want to cut this top surface, and we'll do the bottom one also. We don't actually need all of that, but that'll be fine. All right, so now if we hide the planes, you'll be able to see our little lines going across here, so that those will be selectable when we go to do our simulation. Let's save it again, and let's load up our simulation. So SolidWorks add-ins, I'm going to do the premium I've already loaded it. I'm going to do the simulation premium because I want to do a time, like a transient study. You don't really need that though. You could do a just a static study and it would give you the same kind of thing. I just want this so that I can make some interesting plots. So we'll go over here to simulation tab, new study, and like I said, I'm going to do nonlinear over here, but it's nonlinear static, not dynamic. So I'm basically, I just want a time variable is all I want. So we'll do that. We could have renamed it something if we wanted to. Let's give it a material. So this might, no, it didn't take, I'm going to do the alloy steel. I'm going to do the plasticity von Mises. That really shouldn't matter with the amount of deflection I'm going to apply. We're basically going to bend it down a 1/2 inch. Remember, the way these tests work is you're loading a certain rate, so a speed, 0.001 inches per minute or 0.01 inches per minute or whatever speed, and you're actually just applying a displacement, and you're measuring how much force you're applying, and you're measuring that displacement with most of these type of tests. So that's what I'm going to do, is I'm going to apply a displacement to it. So let's go back over here. Oh, not there. Let's go back to SolidWorks. So I'm going to, yeah, and the plasticity just lets it do, like if there's any kind of thinning out somewhere. That really is not going to be an issue in this test like it was in the tensile test though, but I just want to do it this way. It would be pretty much exactly the same if we did the static, regular material, static simulation. I think it's just the perspective there, but it looked kind of like our middle line wasn't in the middle, but I think it is. All right, so let's apply our loads and constraints. So let's look at our pictures again. So if you see here, it's not really clamped down anywhere. It's just sitting on these round bars. I do need something to clamp it down. So how I'm going to model this is basically treat like this side over here might be a pin, and treat this side like a roller, and then this will be just a vertical displacement in the middle. If I treat both of them completely fixed and I try to push down in the middle, then what will happen is it will want to get longer. The bottom side's in tension, but it can't because it's locked in place, and so that'll multiply the stress that it's actually experiencing. So I do want a something that models a simply supported beam where there's a pin and a roller. So I do want that. I keep going to the wrong thing. So let's do our supports. This not perspective thing is, there we go. That was messing with my visual stuff. All right, fixed geometry. This little line right here is the split line. I'm going to fix that point or that line in space. So that's going to be my pin. So it can't move up or left or right or in and out of the screen. It could rotate about it, and that's okay. It's like acting like a pin. So we'll do that. And then on the other one, we're going to make a roller. But we're not going to do it the way you might think. So there is a roller right here. That's not going to do exactly what I want. This is more like a roller, but I have to apply that to a face somewhere. And that's not what I want. I want fixed geometry again, and I'm going to fix the line. So this little line is kind of like the contact point between the roller or the round bar that it's sitting on and the element being tested. So that line that I have on my model here is simulating that contact point. Now right now I've got it, you can kind of see, I guess I could probably make the arrows a little bigger. Let's make them way bigger, like 3 times bigger. There they go. Now you can see them. So you can see that it's fixed in X, Y, and Z, and I don't actually want it to do that. I only want it fixed in Y, which is the up direction if you look down in the bottom corner over here. So what I'm going to do is go to Advanced, and I'm going to say that I want to apply it to that line, which is already selected there. This is going to give me a reference plane. So I'm going to reference this plane over here. and I'm going to make my translation. They're in millimeters, but they're going to be 0, so it's fine. And then I have to find the one, like so. This one, this button here, fixes it in the Y direction, which is what I want. And I can, I can recreate where I was before, where I fix in all 3 directions, but I only want it to support it like a roller would. I want it to be able to slide or roll over the top of it. So that'll work. So now I've got the roller there. This one, let's go ahead and edit this one to have the larger symbols also, because it's easier to see. There we go. There we go. So I've got this end totally fixed, this end supported in the Y direction like a pin and roller. Now we're going to put not a force in the middle, we're going to put a displacement. So we're actually going to make that a fixed, well, advanced fixtures. Do I want to do advanced fixtures? Well, yeah, you could get to the same place from the fixed geometry, but I'm going to use reference geometry. So I'm going to use the line right in the middle, the split line. That's why I made those split lines with the planes. My reference, I'll just reference this same endpoint in plane last time. Now, the translation, instead of being 0, I'm actually going to apply a translation. And I got to figure out, well, let's also increase the size of our symbols so I can see them. Let's see, is it going to be this one? Nope, not that. That one? Yes, except that's going the wrong way. We want it to go down. And let's do a 1/2 inch. There we go. So there's our displacement, which normally in our machine we would use to measure the force. So that looks good. And that's all we need. It is completely constrained, so it can't move around, it can't float freely in space anywhere. And it's constrained with a pin and a roller, and it's got a vertical displacement in the middle. I think we can just right click, and we have a material applied to it. Right click on mesh, I missed it, and we'll just mesh and run. I didn't change I think it's doing a 1 second interval. So it's going to simulate it enough times to simulate 1 second. It is going to show intermediate steps. So there's one of them, there's the first one. So we can kind of see what it's thinking as it's going. This is not going to take very long. I didn't, make a very dense mesh or anything, and it's not very complicated. If you just did a plain static study, it would finish in, 10 seconds or less. Maybe not even 10 seconds. Because this one is doing multiple iterations and it's finishing pretty fast. It's done 9 different, you can see the time step right here. It's on the 9th. There's the 10th iteration through this thing. And it should be done. All right, so usually the first thing you want to do with one of these is right click and animate it to see if it's doing what you anticipate it doing. So let's slow it down a little bit. There we go. That looks right, Let's see if I can get on the directly straight ahead view. There we go. That looks like if I had, whoops. If I had one of these things, well, you can even see that one's bending just like our simulation is. They're all kind of doing, that one's a little bit different there because it's a giant piece of concrete with rebar in it. But it is looking like what we anticipate it should look like. So that seems good. So we can look at our stresses. We can cycle through the different plot steps. Let's actually create, let's edit our stress plot, or maybe we'll make a new stress plot. So that, remember, these are simulating a beam and bending, and we've been talking about how there's tension on the bottom, well, tension on one side and compression on the other side. Let's see if we can see that. So if von Mises stresses are a combination, but if I isolate just the X, so the X-axis is the longitudinal axis of our beam here. So if I just isolate that one, let's put it in KSI, and Now, look at it. I can see red on the bottom, blue on the top. Now SolidWorks here is, red is showing positive numbers for tension and blue is negative numbers for compression. For whatever reason, they're maxing out at different numbers, a little bit different numbers. That's probably because I actually applied the force. Notice the blue, the compression on top is a little bit higher than the tension on the bottom. The way I applied the force is I applied it to a very thin line. So that is creating a little bit higher stress on the top because it's not only just bending the beam, it's crushing it a little bit. Let's see if we can look at inside view here. So let's do a section clipping and let's clip through the middle somewhere. Let's see if we can get that kind of zoomed in and animate it. Now I'll have to zoom out a little because it's going to be off the screen when it starts. So there, it's relatively slow. Let's slow it down some more though. So you can see the green is zero stress pretty much. And then you can see the compressions develop on the top and the tension develop on the bottom, and kind of still low zero-ish stress in the middle of the stack. So that's kind of what we're talking about when we do the tension on one side and compression on another side. You can actually see it there. Let's create another plot. Let's do a time history plot. Okay, let's pick a node. Let's do the bottom though. Let's pick not the split line. I want one of these nodes. There we go. So we got a point right kind of in the middle of it. I actually don't want this other point, but I don't know how to get rid of it. There we go. Oh, no, I think I highlighted that. Didn't want to isolate it. I wanted to... It'll be fine. We'll get two plots. It's fine. So we're going to do a plot, and we will plot the stress in KSI. Over the full time range is only 1 second. And we get this plot. So the blue one is the one I selected. The red one is node 1, which is not what I selected. So this is interesting. It kind of linearly increases and then it maxes out. So we have to think about, well, what is going on here? It maxes out around 90 KSI. So if I look at my material properties, so here's our material where we applied it over here. And if I right click and look at our details, we look at our details here. If you look at our yield strength, it's 90 KSI, 89,985 PSI. And that chart is basically showing us a zoomed in piece of loading. This is the linear region. And then I hit the elastic region and now it's just stretching. I'm actually not sure what would happen if we increase our, well, let's increase our deflection amount. And at some point it's going to have to break. It'll just fail the simulation. Let's see, that's this one. Let's edit it to make it deflect 1 inch. This might take a while. I don't know. If it takes too long, we'll shut it down. But let's see how long it takes. So the first 10 steps should be the same as what they were before. But after that, at some point, it's going to go beyond yield and it'll probably end the simulation, because it would be a fracture type thing. And since we have the plastic model on, we might actually can watch it neck in the middle here somewhere. So we're on step 6. Now we're on 8 already. Oh wait, I have 2 of these. Not sure why I have 2. I think that's just a redraw thing. There we go. So there's step 10. So last time it finished at step 10, but I told it to keep going further past 1/2 inch and see how far it's going to go until it either gets to an inch of deflection or it says it can't go any further because it can't figure out what would happen. Well, I think it's going to make it all the way to an inch of deflection. It did. All right, so let's see if we can... You know, it's hard to tell. You can see some weirdness in there. Probably some of that, though, is the effect of having that line where we put the load is probably why it's doing that. That could also be, you know, that top part is getting pushed together, and it could be that it's, you know, buckling there on the top. Can't say for sure why it's doing that particular thing, if it's part of the line or is actually modeling some buckling in there. Our stresses are higher now, a good bit higher. We have red on both sides here. Oh, because I'm not showing tension and compression anymore. Now I'm just showing magnitude of stress. Let's see. Let's see if we switch it over to tension and compression, what they look like. Edit definition. And let's do just the X in KSI. Yeah, see, I think that little bump there could just be an artifact of having the line there, but it might not be because it's only at the edges. I'm not sure. But you can see our compression on top, and these numbers are actually, those are about the same as they were the last time because we reached the yield strength. So we didn't actually get beyond our yield strength. You know, it stayed at yield. It didn't actually go into any kind of fracture type stuff. So that's kind of interesting. Now let's drop this back down to only 1/2 inch of deflection. So let's drop that back down, and let's look at some of the things you might do wrong. So one of them is you might go in there and you might fix both. Let's see it. That's the, yeah. Let's delete this one. I think it's a little laggy. Delete that one. Yes, and let's add another completely fixed geometry. So you might think, oh, I should just fix both of these lines. So let's simulate that and see how it changes. I assume it'll still take the 10 steps. I don't really know. We'll do one more bad simulation and then we'll do our web work problem. Because there's two relatively common mistakes you might make with this simulation. And so we'll look at both of those and see what to look for. Part of these simulations is knowing what to expect and then looking for that particular shape. Now, maybe not necessarily the magnitude of stresses and things like that, although you should do some rough hand calculation on stuff like this to make sure you're in the ballpark. But I'm thinking more of the deformed shape. Oh wow, it did a lot more time steps. It's up to 16. But what we changed here is we fully constrained both of those lines, and we're still pushing down in the middle, and that bottom layer is trying to get longer, but it's locked in place also, and so it's having a hard time figuring out what to do with it. It's done twice as many time steps as it did when I set it up correctly. Still hasn't taken, I mean, it's at 2 minutes, so it's still not like it's taken an excessively long amount of time to simulate. All right. Now look at the weirdness that we have now. So see these discontinuities here? Those should probably give you a clue that there's something weird about this simulation. So let's animate it. Notice it looks normal until you get to about there, and then it starts, that's where it wants to start yielding, and this bar is locked in place, and whereas when we set it up correctly it was allowed to slide here, but it does some weird stuff when it's locked in place. All right, so those discontinuities in the slope should give you some idea that that's some maybe not right. Need to check on that. All right, another thing you might do is, well, what if we didn't do fixed geometries like this? Yes. Okay. But we did, maybe we did a fixed face over here, and then a fixed roller over here. So we've got like a really wide pin and a roller. This one should run faster than that last one did. Oops. So we have something like a pin and roller. We actually have one side that's called a roller, so that seems like it might be what we would want. The difference is that we fixed faces instead of just these lines like we did the first time. And you can already kind of see what's going to go wrong here. You're starting to get that S-shaped curve here where it's acting like those ends are clamped down instead of just pinned or sitting on a roller. So you can kind of already see that, well, that doesn't look right anyway. That's what I had the picture of here. You know, you can definitely see the S shape in there. In this one, I actually had applied some little supports instead of just applying the loads directly on the beam. But there's that S shape that we did not expect to have. You would expect if it was just sitting on the supports, you would expect it to, where's our, oh, here's a good example. Well, that's too small to see. Well, you expect it there. See how it just continues out past the support without staying flat there. All right, so that should give you enough to run a simple 3-point bend simulation in SolidWorks for Lab 2. SolidWorks is back running. It went down for a week there with the license server, but it's back now, so you should be able to do that. We actually have exam 2 tomorrow, though, so that's probably more important. This will be due quite a while from now. So I'm going to close SolidWorks. Don't need to save any of that. And I had said that we're going to work on this guy a little bit. So let's copy this and see what we can come up with. All right. Now, this part of this problem is that we actually want to find the reactions and some bending moments at different points. I'm actually not so the stress at different points, all that. Moment of inertia is the one that actually makes this problem somewhat difficult. All this other stuff's pretty straightforward, but it depends on the moment of inertia. So let's work on that and see if we can get this moment of inertia to solve. All right. So what I've got is a weird shape. First of all, it's a pie-shaped piece of a circle, and that's the cross-section of my beam. So I definitely don't know offhand what that moment of inertia is going to calculate to be. So we need to, did I not click it? There we go. We need to get our centroid table. So we need that one. And we need our moment of inertia table. So there zoom in. There is the little pie-shaped piece for finding out where its centroid is located. And then here, at the bottom, is the same pie-shaped piece, but it's the moment of inertia. All right, so I've got a cantilever beam, has this sector for a cross-section, supported at A, got some loads on it. Dimensions of the beam are shown here. And let's see if we can work out this thing's moment of inertia. So, oh wow, oh, hold on. I didn't even think about this. The, where did it go? The touch screen is on, which is always a difficult issue to deal with. So I need to reset that because that's going to be a pain to deal with. Let's see. Hold on. Okay. Still thinking. There we go. All right. It's just too hard to write on this while it's also tracking my hands. So I don't want to do that. All right. So let's draw our little cross section, but bigger, not like that. Why is it? There we go. Oh, I just want to draw regular. We'll get it all together here in a second. All right. So first thing we need to know is where's the neutral axis. So where, it's going to be somewhere in there if we were to measure from an x-axis down here. So we need to know that distance like that. Okay. I do have some dimensions that they give us. They gave us basically lowercase d is the radius of this thing, right? From the center point at D to the peak at E. So 40 millimeters. So this had to go around the thing there. 40 millimeters. What else do they give us? They give us C as 28 millimeters from, I don't like crossing all these lines, but that's what we got to do. Okay. They gave us that. So we do know a couple of things here. We also know that this line is 40 millimeters because it's also a radius. We know that this side is 14 millimeters just because it's the center of our little arc here. So we almost have a triangle that we can work with. One of the reasons I need this triangle is, let's look at the centroid. The way they also look, they've got this picture here is rotated 90 degrees from what I'm actually drawing here. So if I were labeling everything, I actually need to rotate 90 degrees. So x sub c, what they have labeled as x sub c is what I have labeled as the height of the neutral axis. That's the same dimension. And they say x sub c is, I'm just going to copy it. All right, it was buffering, so I wanted to, I'm not sure what the last screen was, but all I did was I went and grabbed this equation and I made the point that x sub c is the dimension that I need right here as a neutral axis. I copied it, and then I made the other point that alpha in this equation is in radians, it's not in degrees. All right, so for me, x sub c, which is the location of the neutral axis for me, measured from the very bottom, that point down at the bottom, is 2r, the radius is 40 millimeters for me, times sine of alpha, which alpha is this angle. Let me get some help here on making this thing. So if we had a little deal here, this is alpha. Okay, so if that's alpha, then this is also alpha. That's alpha. And I've got a bit of a triangle here. You know, this little guy is basically a right angle triangle. And I've got the hypotenuse of it, and I've got the opposite side of alpha, so I should be able to do sine of alpha equals the opposite side, 14 millimeters. Let's see, 14 divided by 40, and I want the inverse sine of that is 20.49, but that's degrees. So, and now that would be fine when I put it in as sine of alpha. I could do sine of 20 degrees, and that'd be okay. But when I do the divided by 3 alpha, that alpha in the denominator needs to be radians. So the numbers I need to put in here are going to be, the neutral axis is at 2 times 40 millimeters times sine, and I can do 20.49 degrees here, but I need to do over 3 times, and then I got to convert 20.49 degrees into radians, which is multiply times pi and divide by 180, right? 0.3576 radians. So 2 times 40 times sine of 20.49 divided by 3 times 0.3576. So I get that this distance from the point to the neutral axis is 26.1 millimeters. So this one. Oh, wait. Yeah. No, yeah, that's what I get. Not the length of that side that I drew of the triangle, just the distance to the neutral axis. It's kind of, maybe I should put this 26 over here. There. More like that. There. Maybe that's clearer. All right, so we have that now. We know where the neutral axis is at, so that's good. Because we want to calculate the centroid, or well, the moment of inertia, about the centroid, or which is the neutral axis. So that's going to be labeled IX about the centroid. That's going to be labeled this one. You got to figure out which one are we talking about here. I've got, oh no, that's just, oh, this one had the location of the centroid on it right here. IX, and I've got IY. So I actually don't have the moment of inertia in the direction I need it about the centroid. So I've got to do a little bit of parallel axis theorem stuff. So I do have this equation. Hopefully I'm getting them all right. So I've got this, IY. But notice their y-axis is the same orientation as when I rotate the shape into the same position that I have the shape. That's the x-axis that I'm using. So that would, this equation that I've got here, this equation would give me the moment of inertia about what I have on this picture as the x-axis. Now I actually wanted about the neutral axis, but we'll get there. So let's see if we can start plugging in some things here. So this will be I about the neutral axis equals R, which we have as 40 millimeters, to the 4th over 4. There's a theta that's not part of like a sine, so that's the one where I need the 0.3576 version, how many radians it is. plus 1/2 sine of 2 theta. Now I do need to make sure that theta, yes, it's saying that they used alpha when they were talking about the centroid. They're talking about the same angle, but on this picture they're using theta. So 2 times theta. Here I can use the degrees and just do sine of 40 degrees, 41 degrees. So that is the moment of inertia about the x-axis that I drew, plus the area of this thing. Do they have an equation for area? Yes. Theta r squared right here. So theta is the going to need to be in radians again. 0.3576 times r squared. That whole thing squared, right? Yes. That's a, and then y squared. So times y is the distance between the axis where I currently have the moment of inertia, so the x-axis, and the axis where I want the moment of inertia, the neutral axis. So that's that 26.1 millimeters, and that's squared. So this is this left-hand side is just the moment of inertia, and the right-hand side is plus a y squared. So let's see if we can possibly get this thing to come out correctly. That's a lot to keep track of, but let's try. So I'm just going to do it in pieces. This first thing is 640,000 millimeters to the fourth. And then I've got, let's do sine of 2 times 20.49 degrees divided by 2 plus 0.3576. So times 0.6855. There's no units on that one. And we'll close that. And then plus the 40, let's see, I got to get this one right. Hold up. Theta times r squared, not theta r squared. So theta in radians, 0.3576. So this part over here is 1,253.37. The units on that should be millimeters to the fourth. Moment of inertia are in units to the fourth, so that looks good. Let's do our 640,000 times 0.6855, and then add on our 1253.37, and let's see what we get. 439,973.37 millimeters to the fourth. These are always kind of worrisome to me because we're about to plug it into WebWork and see if we got the same thing as they got. All right, what was it? 439,973.37. Does it want units on here? I assume. So be sure to include units with your answers. Millimeters to the fourth. Let's see. It's a high chance that we're going to have some errors, but let's check it out. And we got to log in. Oh, whoa. Whoa. Newton meters. Did I plug it in the wrong spot? Oh, I did. I put it in. Whoops. Sorry. Let's cut that from there and put it in here. Whoa. What did we do wrong? All right. Let's see what we might have done wrong here. R to the fourth over 4. Did I forget to divide by 4? 40 to the fourth divided by 4. That looks okay. Did I forget to multiply by 0.6855? No. R to the fourth over 4. There's no good way to test anywhere in between here, is there? Because we're off by a factor of 10. They're millimeters to the fourth, yeah. 28, so that should be okay. I wonder if that's just why people were asking about this question, is because there's something. I don't think there's anything wrong with it, though. I think there might be something wrong with what we did as our process. Let's see. We tried to get alpha here. Hold on, let me see this. 0.3576 times 180. That's 20. That should be right. Okay. Sine of alpha would be 14 over 40. Yeah, that looks okay. Did we... That should be okay. 2 times r. R should be 40. Times the sine of 20.49. I'm just going back through some of the calculations here to see if there's some... That's same. And the 26 for the location of neutral axis seems reasonable. That seems like a reasonable number, so I'm not too worried about the neutral axis not being correct. The problem is when I do r to the fourth. Let me look at our moment of inertia chart again. All right, so their version of y is should be what we need, because ours is rotated 90 degrees from this picture. I wonder... r to the fourth over 4 theta 1/2 sine 2 theta, that looks all right. But we definitely get a very different number than what they have. When you do 40 to the fourth, that's the problem. Because that's a huge number. Then divide by 4, that's not that much smaller. And we're already larger than what they have as their whole answer. So let's just do that part of it again and make sure I didn't do something wrong there. Sine of, well, but it's going to add, hold on. Yeah, that number alone is larger. I'm not seeing where this works out to the answer that they have over here. Maybe I did something, looked at something wrong here. 28 millimeters. B. Oh, that's those distances. Those are fine. D is the radius, right? Yeah, that's radius. C is from one point to another. That looks fine. And it's 28. Moment of inertia about the neutral axis. That looks fine. But when they want their answer in there, they have got 48,000 millimeters to the fourth. And I've got 440,000. Well, I thought I would help out with this problem, but I'm not seeing where I have something wrong. So one thing that I'm not sure about. So when you look at the moments of inertia chart, usually like the x, ix or iy, well, none of these have iy actually. They're all, that's what this one does. They are about the centroid. So that's pretty normal. This one, iy, that's not the centroid, so I should add the parallel axis there, which is pretty small anyway, so that doesn't seem to be the issue. really don't know why we're getting such a different answer from what they have, and I doubt I can find it in the code for it. I mean, it's going to be hard to figure out what. I mean, there it is. The moment of inertia of the neutral axis, they're subtract. That would be weird if that's the way that they did that. C bottom. C bottom is 2 centroid to the bottom, I think is what that means. That doesn't make much difference the way, but wow. Let me see something real quick. Okay, if this is what it is, then that's a super tricky thing. 40x squared. And I can I don't know, we'll see. Times 26.1 x squared times 0.3576. All right, so I don't, for one reason, I don't even know why I wrote this number down. I wrote it down incorrectly. 38961.1 millimeters to the fourth. I think I didn't do this squared right here when I did that one. That's probably what's going on there. And then what I end up with, 640,000 times 0.6855. That number is 438,720. That's a 2. And this number is 389761.1. And if I subtract those, yep, 40. So, oh, not that one. All right, this I'll have to explain this, and it is what I was talking about. All right, so let's see. Let me see what this says. Do you think you could also explain how unevenly distributed, if you don't, unevenly distributed load? You might have to give me a little more explanation of what unevenly distributed loads you mean. Like finding their centroid or something, but I probably can. But let's explain what's going on with this one. This is a weird one, and it does have to do with this. So, or if you have a webwork problem that has an unevenly distributed load on it, maybe I can just go straight to that one. So here. So notice all of these. IX is at the centroid. IX is a centroid. And we have the X primes over here that are at the base of the object. For whatever reason, this one is different. On the y-axis anyway. The x-axis does go through the centroid, but the y-axis doesn't. And what they have done is this equation IY is actually the moment of inertia about the point, but it already has the parallel axis theorem applied to it. Now, how you would know that, I don't actually know. So, based on this chart, you wouldn't actually know that, except that it's not at the centroid. So maybe you would know that, oh, this is the moment of inertia about the point. It's not at the centroid, so it already had the parallel axis theorem applied to it to move it from the centroid down to the point. Why they didn't just give it to you at the centroid and let you apply it to get it down to the point, I don't know. But maybe it's complicated. I don't know. For whatever reason, this moment of inertia IY has the parallel axis theorem in it. So basically this equation IY is this is moment of inertia in the y direction, or parallel to the y-axis, about the centroid plus AY squared. So in order to get this part, which is what I want, we have to take this equation and subtract off AY squared. So that's why we need these negative signs here. And then we get down to the actual moment of inertia about the centroid. That's not, I can see why a lot of people would miss that. I didn't, when I was going up through here, I was trying to make sense of, the IXs were all at the centroid. And this one, for whatever reason, they did IY, and they did it at the point down here. It would have been clearer maybe if they called it IY prime, something like that. Because all the primes are the ones that are at the base, but they didn't. And so this little equation IY actually has the parallel axis theorem already applied to it. All right, so you're looking for a, a beam problem that has a distributed load on it. So let's see if we can get over to some of those. That one, but you want it unevenly distributed. So actually none of our beam problems are going to have unevenly distributed loads, so I'm not sure which ones you might be thinking of. I'll look and see if I can scroll through any. Yeah, these are all evenly. Oh, here we go. 14, problem 3. All right, let's look and see what that's about. Where did 14 go? There we go. Oh, okay. So, figure out the reaction force with tape. Yeah, this is a good one to do. All right, so got this, and it's got a lot of parts to it. It wants us to find the reactions, the moment at A, some strengths and all that. It's got a much simpler cross-section. Actually, the other one was a simple cross-section. It was just a sector. It's just difficult to work with. But what we do with this is, let's go over here. And so the tapered load is trying to simulate something where it's heavier on one end than another end. So this could be like there's sand piled up on this platform, and it's more sand towards the wall than there is towards the free end of the beam, and so it's heavier on one end. It's kind of what it's simulating. Or maybe like a swimming pool where the water gets deeper as you go further out, something like that. So there's force at one end and the other, and it gradually tapers off. So what we're going to do with this is, in order to deal with it as far as calculating equation stuff, we're going to do, what does it want us to find? Reaction at A and moment at A. We'll do those first. So here's our beam, and then we've got our distributed load that's tapering off to 0. And it starts, for me, the highest point is 37 pounds per foot, and then it goes to 0. And we've got A is 5.3 feet. And this is a fixed support, so this is a cantilever, and it's a moment at A. Okay? So I drew a clockwise moment. Clearly, it's going to need to be a counterclockwise moment, but to keep the beam from tilting downwards. But I drew it as clockwise, so that's fine. So what I want to do with the distributed load, in order to put it into an equation like summation of moments or summation of forces, then it's going to be a lot easier to find the centroid of the distributed load and put the whole thing right there. So the centroid of a triangle, if we just had a triangle, actually we have the centroid chart pulled up. So let's find the triangles over here. There it is right there. So the centroid of a triangle from the pointy end, the tapered end, to the centroid is labeled x sub c. It's 2/3 of the base. All right. So that would be this distance is 2/3 of the base of our whole triangle, which is a distributed load, is 5.3 feet. Okay, so that number is 2 divided by 3 times 5.3. 3.533 feet. Okay, so that makes this distance 5.3 minus that number. 1.7 and a bunch of sixes. We'll just do 7.7. Okay, now when I write the equation, summation of moments about point A. I'm doing point A because I want the AX and AY. Well, AX already goes to 0. We already know that. But I want AY to not be in this equation so that I can only solve for MA, the moment at A. And then we can come back to AY. I think they called it RA in their... Yeah, they call it RA. But what I've labeled is AY. So now I can just write... oh, we need to know the value of this thing. So to calculate the value of the lumped load, the blue arrow that I drew pointing down, it's just the area of the triangle. So the triangle has a height of 37 pounds per foot and a base of 5.3 feet. It's a triangle, so I need to divide base times height divided by 2. So 98.05 pounds when you multiply pounds per foot times foot and then divide by 2. So I take that as my point load, but it's really just a lumped representation of the distributed load. 98.05 pounds multiply times its moment arm from point A. Point A is right here at the wall. Of 1.7. All right, just waiting for it to catch back up from buffering. So there we are. We're back synced up now. So there's our negative 177. Now this is actually 177.3 foot-pounds counterclockwise. I don't know that they want us to put clockwise or counterclockwise in on this problem, so I'm just going to put the 173 and see if it likes it. 5 foot-pounds. And I don't know if it wants, how it wants foot-pounds in there. So I'm going to kind of cheat a little bit, as usual. 173.22. So whenever I rounded off that 05 number, there's threes. This is a 6, 7, or 7. No, it's a bunch of sixes actually. So I did a little bit of rounded in this 1.77 number. Did a little bit of rounding, I guess, in the maybe in the 05 number. I don't remember if I rounded that one much at all. But instead of 1.73.55, they want 0.22. So that's fine. Again, on exams and stuff, that's not going to be a problem because the exams are either going to be multiple choice or they have a wider range for their errors, rounding errors. So the reaction at A, if I look at this, AY equals this lump load, so it's just 98.05 pounds. And then they want the stresses. At this point, I don't know that you need anything else on the flexural stress part because you were asking about the distributed load, the unevenly distributed load. Hard to say. So the compressive stress, it wants the compressive stress wherever it's maximum. Well, let me show you. It says maximum tensile and compressive normal flexural stress. And so that means we would have to find where the bending moment is largest. So you could draw the shear and bending diagram, but also remember for cantilever beams, this is a cantilever beam, the maximum bending moment is at the wall. So this number, this 173, that is the maximum bending moment. Oh, good. It looks like it says it makes some more sense now, so that's good. So that 173 foot-pounds is going to be the bending, well, 0.22, not 0.55 like I had. That's going to be the M in these flexural stress equations over here. All right. All right, tomorrow we will get on Zoom. I'll put the Zoom link in Moodle and in Discord, and we'll do exam 2, and that should be good. If you have any last minute questions between now and then, put them in Discord, and maybe I'll see them and have a chance to reply to them. I'm not sure, but that's probably what we're down to now. All right, I will see y'all tomorrow. Actually, see you in Zoom.